Today, we're looking at section 6.2 in your textbook, and 6.2 deals with finding confidence intervals for the mean when sigma is unknown. So in section 6.1, we were focusing on samples where we knew sigma. The problem with that is that's not always possible, practical, or available. Matter of fact, most of the time it's not likely. When we're looking at a particular set of data, the idea that we would have the value of the population standard deviation is kind of nonsensical unless we have a very small population that we've worked with before. Most of the time, we're going to be operating without knowing what that population standard deviation is. So what do we do if we don't know what sigma is? That's the question that we're going to try to answer here in section 6.2. Well, the whole thing revolves around something called the t-distribution. Now, we've looked at the normal distribution, and the t-distribution behaves similarly to that, but there are some differences. To be able to fully understand the concept of the t-distribution, we really need to define something called degrees of freedom. We've mentioned them in passing before, but we haven't really delved into what they're about. So, what are degrees of freedom? Well, the degrees of freedom are always equal to one less than the sample size. So, degrees of freedom are equal to n minus 1. What is it, though? The best example that I can kind of give you is to think of a room. And let's say there's 30 chairs in the room for people to sit down in. And there's a bunch of people waiting to get in the room in line. And there's 30 people in line. So they decide to let people in one at a time to let them choose a space to sit. When the first person walks in, they have a choice, right? They get to make a choice out of the 30 chairs that are available. When the second person comes in after the first person has sat down, that second person also has a choice. They may not have quite as many choices as the first person, but they do still have choice. And the third person has choices, and the fourth person has choices. We keep going and keep going. And then we have the 29th person. The 29th person comes in. There's already 28 people seated. So there's only 2 available chairs. Does that 29th person have a choice? Yes. They have very little choice, but they still have choice. So they make their choice and they sit down. When the last person enters the room, the 30th person, does that 30th person have a choice? And the answer is no, right? There's only one chair to sit in now. So if that person's going to sit down, that's where they're sitting. They don't get to make a choice. They just go sit in the chair. So when we talk about degrees of freedom, what we're really saying is that as we're arranging data values and putting them in order, like you could think of a factorial problem where we're counting the number of different ways that 10 runners could finish a race. As we go through, there's 10 choices for the first runner to cross the finish line, 9 for the second, 8 for the third. But once the first 9 people have crossed the line, there's no choice as to who's going to be next, right? That last individual has 0 choice. And so all of the other positions in that race, there was some choice as to who was going to cross. But the last one has no choice. So when you have a set that has n objects in it, and you're trying to place them in n different positions, for n minus 1 of them, you get to make a choice. But for the very last one, there is no choice. So there's no freedom where that last one goes. That's what degrees of freedom are about. How many times do you get to make a choice? Well, if you're putting n objects in n positions, you only really get to make a choice n minus 1 times. So let's take a look at the t-distribution itself. So what the t-distribution are is they're curves that are continuous probability distribution curves for a random variable x, similar to the normal distribution, and they meet the following conditions. Just like in the normal distribution, the t-distribution has the mean equal to the median equal to the mode. The t-distribution curves are bell-shaped. They are symmetric about the mean. And the total area under each curve is 1. But the difference is that we're not talking about a single curve here. When we talk about a normal distribution, we're talking about one curve. When we're talking about a t-distribution, we're talking about a family of curves. So the difference between the different curves in the family come from the degrees of freedom. How many degrees of freedom were present when we were calculating these curves? So we can look at an example. These are all t-distribution curves. And what you'll notice is that that black one, the tallest one of all, that's actually the normal distribution. The red and the green and the blue curves, those are t-distribution curves. So what do we notice? Well, the t-distribution curves are always shorter, right? They don't go quite as high at the peak, but their tails are thicker than the standard normal distribution or any normal distribution. So when we get higher and higher values of the degrees of freedom, those graphs tend to become more and more like the normal curve, right? So you can see the red graph has degrees of freedom 3. Then the green graph has degrees of freedom 7. So higher degrees of freedom, and notice its tails are a little bit thinner than the red one, and the peak is a little bit higher. And then when we see the blue one that has degrees of freedom equal to 13, its tail is even skinnier, and its peak is even taller. And so they're kind of getting closer and closer and closer to the actual normal curve. Okay, so what we're going to do with these t-distribution curves is very much like what we did with the standard normal distribution, but it's a little bit different, and there's a brand new table, right? So we saw the standard normal distribution table in section 5.1, and we've been using that consistently throughout the section since. But the t-distribution has its own table. So let me introduce you to the t-distribution table. This is the first part of it. Now, in your printed notes, it's much prettier. There's not as many pages of it, but you can only fit so many entries on a slide. So this is going to be several slides long. Okay. So what's similar about this table and the standard normal distribution table? And the answer is there's a lot of numbers, right? We've got rows, we've got columns, all kinds of values in the middle. What's different about this table, though, this t-distribution table, is that the values that are inside the table don't represent areas or probabilities like they did on the standard normal distribution table. What they actually represent is something more like the z-score, right? When we were finding those area values, we would sometimes look for the area in the table of the standard normal distribution table and then figure out the z-score, right? Well, what these values are is they're like what the z-scores would be to have a particular area in the middle. And across the top where we see levels of confidence, that would be the area that's trapped in the middle. So a level of confidence of 0.90 means that we would have an area of 0.9000 trapped in the middle of our t-distribution curve. And what would the t-scores be to give us that value? Well, it would be dependent on the degrees of freedom, whatever values we would have in this 0.90 row that corresponds to our degrees of freedom. So the table's different, but we're going to use it for the same kind of a thing. We would find the area in the table for the standard normal table and convert back to the z-scores. So with the t-distribution, we're going to use our level of confidence, which is the area, along with the degrees of freedom, because each t-distribution curve is a little bit different. So we have to know the degrees of freedom to be able to do the proper calculation, to find our critical values, which are t-scores. So in the standard normal distribution, we have z-scores. With a t-distribution, we have t-scores. So we have a little example here. We want to find the critical values for a C level of 0.99 and a sample size of 22, n equals 22. So let's take a look at our solution here. We need to know the degrees of freedom before we do anything else. So degrees of freedom are always n minus 1. In this case, the n is 22, so it's 22 minus 1, which is 21. We need that value because that's part of the table processes. Along the left-hand side of the t-distribution table will be the degrees of freedom values, so we would have to have that value to be able to proceed. So then we're going to go to the table, and I've done a little cutout of the table here for you. What we see is level of confidence across the top, and down the left-hand side we have the degrees of freedom. Now, don't worry about the one-tail, two-tail part. We will talk about that in later sections, but for right now, it's not important to us. All we're focusing on is the level of confidence and the degrees of freedom. So, we need to look up the proper value from the table, the proper critical value. So we can find our degrees of freedom, and we said that the degrees of freedom were 21. So here's the 21. And then we're looking for a level of confidence of 0.99. So at the top, we've got 0.99. So where do those two meet? They meet right here at 2.831. So that is my critical value. TC equals 2.831. So remember when we were doing the standard normal distribution and we would find a z-score, sometimes we were interested in the area in the middle. And so we would use plus or minus of that z-score. We're going to do the same kind of thing here. The 0.99 is the area in the middle. So 0.99 on this particular t-distribution curve would be trapped between negative 2.831 and positive 2.831. The t-distribution curve with 21 degrees of freedom has an area of 0.9900 between t equals plus and minus 2.831. So how about a practice problem? Same kind of thing, not too hard. We're just going to find a value from a table. That's kind of where we're starting. We want to be able to do this part of the process before we try to expand it and do more things. So I want you to find the critical values when we have a confidence level of 0.90 and a sample size n equals 20. So do a little work, pause the video, and when you're all ready to hear the answer, press play. Okay, so for our solution here, we're first going to start with the degrees of freedom, because we can't use the table without degrees of freedom. So degrees of freedom are always n minus 1. In this case, our n is 20, so it's 20 minus 1. And 20 minus 1 is 19. So now we can go to the table. And when we go to the table, here's a little cutout of the table for you. We need to locate the row that has 19 degrees of freedom and the column that has a confidence level of 0.90. So the column with a level of confidence of 0.90 is here, so it's right here, right in the middle. And then 19 degrees of freedom comes across, and the value is right there. It's 1.729. Okay, so that's your critical value. The critical value is TC equals 1.729. So that means that on this particular t-distribution curve, an area of 0.9000 is in the middle of the t values plus and minus 1.729. So that's what we're looking at here. We're looking at this idea of being able to find the t-distribution values. Because if you remember right, when we were dealing with the standard normal distribution and we found the z-scores, then we would use the z-score as part of our confidence interval process, right? Because the z-score was part of the formula for computing the margin of error. And we had to find the margin of error to be able to build our confidence interval. Well, the same kind of thing is going to be true here. We're going to need the t-score to find our margin of error, and we can't build the confidence interval without the margin of error. So let's look at our process for constructing our confidence intervals, and you're going to see that it's really, really similar to what we're doing with the standard normal distribution. So the first thing that we're going to do is we have to calculate the degrees of freedom. Again, the reason we have to do that is the t-distribution table is built to have degrees of freedom because each one of those curves is slightly different. So we have to incorporate the degrees of freedom into our table. Next thing we're going to do is find our critical value, TC. And so we're going to do that by using the degrees of freedom along with our level of confidence and finding where those two meet, where that row and that column meet. That will be your critical value. Once we've got the critical value, what do we do with it? Well, we need to construct our margin of error. If you remember right, the margin of error when we were dealing with standard normal distribution was error equals ZC times sigma over the square root of n. Well, with the t-distribution, the error is TC times S over the square root of n. So that's very similar to ZC times sigma over the square root of n. This is TC times S over the square root of n. But it's still a critical value times the standard deviation divided by the size of the sample. So both margins of error are found the same way, right? You take a critical value that we get from a table, you multiply it by the standard deviation, and you divide by the size of the sample. That's true for the standard normal distribution. That's true for the t-distribution. And then how did we construct our confidence interval? Well, we're going to take the margin of error and subtract it from the mean. And then we're going to take the margin of error and add it to the mean. This is very much the same as what we did with the standard normal distribution. It's just we get our critical value from a different table, and the different table has slightly different way that we use it. But once we get that critical value, the rest of the process is very much the same. Let's take a look at an example. The weight of loaded semi-trucks is normally distributed. At a highway weigh station, 25 loaded semis are stopped and weighed. The average weight was 22,500 pounds with a standard deviation of 1,150 pounds. Construct a 90% confidence interval for the mean. So this is the first time that we've kind of done the entire process. So we're just going to go step by step. We just got a 4-step process. We're supposed to calculate degrees of freedom, find our critical value, determine the margin of error, build the confidence interval. All right, so first things first, let's find those degrees of freedom. So in this case, our n was 25, and degrees of freedom are always n minus 1, so it's 25 minus 1, which is 24. So we can go to the table. Here's a little cutout of the table that we're going to need. Our sample size was 25, so the degrees of freedom were 24. So we look for the row that has 24 degrees of freedom. Then we wanted to have a confidence level of 90%. So we go to the 90%, 24 degrees of freedom. So we're looking at 0.1711 for our critical value. Right? So now we've got the first 2 steps of our process complete. Right? We found degrees of freedom. We found our critical value. Now we need to find the margin of error. So we're going to use the margin of error formula. Error equals TC times S over the square root of n. So the 1.711 is our TC. In the original statement of the problem, we were told that the standard deviation for the sample was 1,150, and the sample was size 25. Notice, we're not using 24, which was the degrees of freedom. We're using the sample size, n, not n minus 1, in that denominator. So we can go ahead and divide. Now, square root of 25 is 5, and if we took 1,150 divided by 5, we would get 230. So that's where the 230 comes from, in case you were wondering. We multiply 1.711 times 230, and the result is 393.53. So that's a margin of error. What are the units? Do you know what the units are on this margin of error? Hopefully you realize that this measurement is a measurement in pounds, because when we were talking about the original problem, we said that the average weight was 22,500 pounds with a standard deviation of 1,150 pounds. So whatever units the original problem is in is what our margin of error is going to be in. So the margin of error here is 393.53 pounds. Once we've got the margin of error, we're ready to find the confidence interval. Okay, so the confidence interval is found by taking the error, subtracting it from the sample mean, adding it to the sample mean. So the sample mean was 22,500. So we're going to do 22,500 minus 393.53, 22,500 plus 393.53, which results in a 90% confidence interval of 22,106.47 and 22,893.53. So we're 90% confident that if we were to take all the loaded semi-trucks and find their average weight, that average weight would fall somewhere between 22,106.47 pounds and 22,893.53 pounds. So we have a practice problem. Your practice problem is about tuition costs. So the cost of tuition per year at a 4-year university in the United States is normally distributed. A sample of 18 4-year universities is chosen. For this sample, the mean was $17,400 and its standard deviation was $1,200. Use this information to construct the 95% confidence interval for the mean. So you're going to follow that 4-step process to come up with your value. Let's take a little time, pause the video, and when you're all ready to see the solution, press play. Okay, so let's take a look at our solution. We're going to follow that 4-step process. First things first, degrees of freedom. Degrees of freedom are n minus 1. So in this problem, our sample size was 18. So 18 minus 1 is 17. So we're looking at 17 degrees of freedom. We need to know that degree of freedom value because it's essential to use the table. So now we're going to go use that table. We need to know the degrees of freedom, which we just found were 17, and the level of confidence, which we said was 95%. So here's a little cutout of the table for you. So we find where the degrees of freedom are 17, and the level of confidence is 95%. And so when we look for where those meet up, they meet up at 2.110. So that is your critical value. That's the second step, right? So first step was to find the degrees of freedom. Second step, find the critical value. Once we have the critical value, we're ready to find the margin of error. So the margin of error formula says you're going to take the critical value times your standard deviation for the sample, and you're going to divide that by the square root of the sample size. So we just found the TC value was 2.110. The standard deviation for our sample was 1200, and the n value was 18. So we get 2.110 times 1200 over 18. When we multiply that out, now I put this in a radical form. If you use the calculator, it's not going to come out in the radical form. There is a way to make it do it, but for right now, we can just understand that that's what this would be. If you multiplied it completely out with your calculator, this is what you should get. Now you'll notice I rounded off to 2 decimal places. Why would I do that? Right? This doesn't come out as 2 decimal places. It's actually a much longer decimal because of the square root of 2. So what would cause me to want to round off to 2 decimal places? Because most of the time we round off to 3 or 4. Why 2 this time? The answer is because we're dealing with money. This problem was about tuition costs. Costs are in dollars and cents, and whenever we're talking about dollars and cents, we always want to round off to 2 decimal places, because this represents $596.80. So now we can construct our confidence interval by taking that margin of error that we just found, subtracting it from the sample mean, and adding it to the sample mean. So the sample mean in this problem was 17,400. So we're going to take 17,400 minus 596.80, 17,400 plus 596.80. So the 95% confidence interval is $16,803.20 to $17,996.80. So I am 95% confident that if I was to find all of the tuition costs for all of the 4-year universities and take their average, that average would fall into this interval. So you may be asking yourself a question right now. How do I tell the difference, right? How do I know whether the problem requires me to use the standard normal distribution or the t-distribution? So we have a little kind of flow chart here that I've developed to help you figure that out. So in either case, you got to have a normally distributed population. Then the question that you're going to ask yourself is, do you know the value of sigma? Do you know the population standard deviation? If the answer to that question is yes, then you're going to use the standard normal distribution. You're going to use z-scores. If the answer to that question is no, then you're going to use the t-distribution. Okay, so it's all about whether or not you know sigma. If you noticed when we talked about section 6.1, when we were developing the margin of error using the standard normal distribution, the title of that section was confidence intervals with sigma known. And here in section 6.2, the title of our section was confidence intervals for the mean with sigma unknown. So that's really the deciding factor. Do you know the value of sigma or not? If you know sigma, then you're going to use the standard normal distribution. If you don't know sigma, you're going to use the t-distribution. So let's look at an example. Which distribution would you use to construct the confidence interval for the following? Now, I don't want you to do the confidence interval. I just want you to be able to discern which process we should use. Should we use the standard normal distribution process with z-scores, or should we use the t-distribution process with t-scores? So the problem is, frogs lay hundreds of eggs per cycle. The number of eggs that reach maturity is approximately normally distributed. A random sample of 14 frogs is chosen, and their eggs are tracked. The average number of eggs that reach maturity was 64, with a standard deviation of 7. So the question here is, which distribution do we use? The process, we said, was let's find out if we know sigma. So let's read through that problem again, and ask ourselves, do we know the value of the population standard deviation? Frogs lay 100 of eggs per cycle. The number of eggs that reach maturity is approximately normally distributed. A random sample of 14 frogs is chosen, and their eggs are tracked. The average number of eggs that reach maturity was 64, with a standard deviation of 7. So 7 is the standard deviation, but it's the standard deviation for this sample of 14 frogs. It wasn't said that the standard deviation was 14 for all frogs, just that when we tracked these 14 frogs and looked at their egg production, that the standard deviation was 7. So this is not a population standard deviation. This is a sample standard deviation. So we don't know sigma. Since we don't know sigma, we're relying on the t-distribution for this particular problem. Now again, we're not doing the problem. We're just trying to decide if we can tell which process we should use. Now how about a practice problem for you? In 2004, the standard deviation for all takers of the civil service exam was 7.3 points. The civil service exam is an exam that the government provides to do certain government jobs. So for instance, if you wanted to be a mail carrier, right? So work for the post office, you have to take the civil service exam. So a random sample of 20 test takers is chosen. Their average score was 76. Assume the test scores are normally distributed. Which distribution would you use to construct the confidence interval for this situation? So think about that for a second, come up with your answer, and when you're ready to hear my answer, press play. Alrighty, so when we look at this statement of the problem, there's one word that pops out at me that tells me what I'm doing here. It says the standard deviation for all takers of the civil service exam was 7.3. And the word that pops out at me is the word all, for all takers. When I see that the standard deviation for all takers is 7.3 points, that tells me that this is a population standard deviation. So that is the value of sigma. So we're going to use the normal distribution here because we have a known value of sigma. It doesn't matter how big or small the sample is. A lot of times people say, oh, the central limit theorem says that your samples have to be 30 or more, but it's really about that sigma value. So that means we're going to use the normal distribution for this particular problem. That brings us to an end of section 6.2. So please look on Pearson for your homework and have a great day.